Hello everyone, welcome back. If you're listening right now, help me prove something wrong. My mother once said, I'd never reach 1,000 subscribers. But I've always believed stories like this deserve a quiet place to land. If you feel that too, you're already proving her wrong. Subscribe to this channel if you'd like to keep these gentle stories alive. And now, let's continue. Right now, as you're settling in, your watch is ticking. 1 second, then another. Time moves forward, always has, always will. At least, that's how it feels. But what if I told you there are places in the universe where your watch would slow down, not because the battery is dying, but because time itself flows differently there? Places where 1 hour for you could mean years passing for everyone else. Places where time can almost stop. These places exist. They're called black holes. You don't need to remember everything tonight. You don't need to take notes or think too hard. Just listen. Let the ideas wash over you. If you drift away, that's exactly what should happen. We're going to talk about something strange and beautiful, something that changes how we think about one of the most basic things in existence: time. Think about your day today. Morning came, then afternoon, then evening. Time passed. It always does. We measure it with clocks, track it with calendars, feel it in the changing seasons and the birthdays that keep coming. Time feels solid, dependable. The one thing that never changes is that time keeps moving forward. But time is stranger than it appears. Here's something real, something that actually happens every single day. There are clocks orbiting Earth right now, up in space, aboard satellites, GPS satellites, the ones that help your phone know where you are. Those clocks tick slightly faster than the clock on your wrist. Not much faster, just a tiny, tiny bit, about 38 microseconds per day faster. That doesn't sound like much, and it isn't really, but here's the interesting part. If we didn't account for that difference, your GPS would be wrong, not by a little, by several miles. Within a month, it would be useless. Why do those clocks tick faster? Because gravity up there is weaker than gravity down here. And weaker gravity means time flows just a little bit faster. This isn't a guess. It's not a theory that might be wrong someday. It's measured, proven, happening right now above your head. Time doesn't flow at the same rate everywhere. When Albert Einstein figured this out more than 100 years ago, it seemed impossible. Time was supposed to be constant. The same for everyone, everywhere. That's what made sense. But Einstein showed that time is connected to space, not separate from it. They're woven together into something called spacetime. 4 dimensions, the 3 of space that you can move through, left and right, forward and back, up and down, and 1 of time. Spacetime isn't just empty nothing. It has shape. It can bend and curve, and what bends it? Mass stuff, matter. Imagine you have a trampoline pulled tight, nice and flat. Now put a bowling ball in the middle. The trampoline dips down, right? It curves around the ball. The heavier the ball, the deeper the dip. That's basically what massive objects do to spacetime. They curve it. The sun curves spacetime. Earth curves spacetime. You curve spacetime, though only a tiny, tiny bit. The more massive something is, the more it curves spacetime around it. And here's where it gets interesting. When spacetime curves, time changes. The deeper you are in that curve, the slower time flows. Not slower in a way you'd notice personally. Your own heartbeat, your own thoughts, your own watch, they all seem normal to you. But compared to someone far away from that curve, far from that gravity, your time is moving more slowly. This is gravitational time dilation. Time dilating, stretching out because of gravity. You've probably noticed your breathing has gotten slower while you've been listening. That's good. That's natural. Your body knows what to do. We're going to explore something that seems impossible, but it's real. We're going to think about black holes and what they do to time itself. And as we do, you can let your mind wander. You can let yourself relax deeper. There's nowhere you need to be, nothing you need to do. Just listen or don't. Either way is fine. Black holes are places where spacetime curves so extremely that time does something truly bizarre. But first, what is a black hole? Most people think of them as cosmic vacuum cleaners, sucking up everything around them. That's not quite right. Black holes have gravity, just like Earth has gravity, just like the Sun has gravity. From far away, a black hole's gravity is no different than anything else with the same mass. If you replace the Sun with a black hole of the same mass, which couldn't actually happen, but imagine it, Earth would keep orbiting exactly as it does now. We wouldn't get sucked in. The gravity at our distance would be identical. What makes black holes special isn't that they pull harder from far away. It's that you can get much, much closer to all their mass. Here's how they form. Stars are massive. Our Sun, for example, has enough mass that you could fit more than 1 million Earths inside it. Some stars are even bigger, much bigger, 10 times, 20 times, 50 times the mass of the Sun. These giant stars burn bright and hot, but nothing lasts forever. Eventually, after millions of years, they run out of fuel. When that happens, there's nothing left to hold the star up against its own weight. Gravity takes over. The star's core collapses inward, fast. In less than a second, all that mass falls toward the center. The outer layers explode outward in what we call a supernova, one of the brightest events in the universe. But the core keeps collapsing. Smaller, denser, tighter. If the core is massive enough, nothing can stop it. It collapses past being a dense ball of neutrons. It keeps going. It squeezes down to a size smaller than a city, smaller than a mountain, smaller than you. All that mass compressed into an impossibly tiny space. The result is a black hole. Imagine squeezing Earth down to the size of a marble. All the oceans, the mountains, the core, everything compressed into something you could hold in your hand. That marble would still have all of Earth's mass. But now, all that mass is concentrated in a tiny space. If you could get close to that marble, very close, the gravity would be intense, because you'd be near all that mass without thousands of miles of planet between you and the center. Black holes are like that, but far more extreme. All the mass of a massive star compressed into a point, or very nearly a point. We call this the singularity. Around that singularity is a boundary, not a physical wall, not a surface you could touch, just a boundary in spacetime itself. We call it the event horizon. The event horizon is the point of no return. If you cross it, you can never leave. Not because you're being pulled by some mysterious force, but because spacetime itself is so curved there that all paths lead inward. Even light, the fastest thing in the universe, can't escape. That's why black holes are black. Light goes in and never comes back out. You're doing fine. Your eyes might be heavy now. That's all right. You don't have to keep them open. You don't have to focus too hard on every word. The universe is full of these objects. Millions of them, just in our galaxy alone, most formed from dying stars. They sit out there in the darkness, warping spacetime around them, bending light that passes nearby. And bending time. There are different sizes of black holes. The smallest ones we know about are a few times the mass of the Sun. These are stellar black holes formed from collapsed stars. There might be millions of them scattered throughout the Milky Way. Then there are the giants, supermassive black holes, millions, sometimes billions of times the mass of the Sun. We find these at the centers of galaxies. Our own galaxy has one. It's called Sagittarius A star, though we usually just write it as Sagittarius A with an asterisk. It sits 26,000 light-years away from us, right in the center of the Milky Way. It's about 4 million times as massive as the Sun. Sounds terrifying, maybe, but we are perfectly safe. We are very, very far away. We orbit around it, just like Earth orbits the Sun, except our orbit takes about 230 million years. We've been watching stars orbit close to Sagittarius A star, very close. These stars move incredibly fast, whipping around in elliptical paths. From watching their orbits, we can measure how massive the black hole is. We can see how it affects spacetime around it. And we can see what it does to time. This is where things get truly strange. Imagine two people, twins. They're both the same age, born on the same day. They have identical watches set to the same time. One twin gets into a spaceship and flies far from any massive object. No stars nearby, no planets, just empty space. She waits there. The other twin gets into a different spaceship. He flies toward a black hole, not into it. He's not planning to get trapped, just close, very close to the event horizon. He hovers there, using his ship's engines to stay in place, fighting against the pull. From his perspective, everything seems normal. His watch ticks along, 1 second, another second, he breathes, thinks, exists. Time feels the same as it always has. He stays there for 1 hour by his watch. Then he fires up his engines and flies back to meet his twin. When they reunite, something impossible has happened. His twin has aged, not 1 hour, years, maybe decades, maybe centuries. Her watch shows that all that time has passed. She's lived through all of it. She's gotten older, memories have formed. She's experienced all those days and nights. But the twin who went near the black hole, he's only aged 1 hour. His watch shows 1 hour. He remembers 1 hour. This isn't science fiction. This is what Einstein's equations tell us would happen, and we have every reason to believe those equations are correct. They've been tested again and again. They predict things we can measure, and the measurements match. Near a black hole, time genuinely slows down. Your breathing is probably very slow now, deep and easy. The room around you might feel distant. That's exactly right. We're going to think about what this means, what it would really be like, but there's no rush. We have time, all the time in the world. Let's think about this more carefully. The twin who stayed near the black hole, time didn't feel slower to him. This is important. He didn't feel like he was moving in slow motion. His thoughts weren't sluggish. He wasn't trapped in some kind of half-speed existence. To him, everything was completely normal. His watch ticked once per second, just like always. His heart beat at its normal rate. If he snapped his fingers, the sound came immediately, just like it should. From his perspective, nothing was wrong. The strangeness only appears when you compare his time to someone else's time. Someone far from the black hole, where space-time is much flatter, much less curved. From the distant twin's perspective, her brother's watch was ticking slowly. His movements looked sluggish. Everything about him was happening in slow motion. But from his perspective, he was normal and she was sped up. If he looked at her through a telescope, he'd see her watch spinning fast. He'd see her moving quickly, agging rapidly. Both perspectives are correct. Neither one is more real than the other. Time is relative. Here's what that word means. Relative. It means that time isn't absolute. It's not the same everywhere. It depends on where you are and how you're moving. There's no universal clock ticking away the same seconds for the entire universe. Every observer has their own experience of time, and all of them are equally valid. This feels wrong, doesn't it? It feels like time should be the same for everyone. That's how we experience it in our daily lives. Your watch and my watch tick at the same rate, more or less. We agree on when things happened. But that's because we're all in very similar gravitational conditions. We are all on or near Earth's surface. The differences in time flow are so tiny we can't notice them without extremely precise instruments. Near a black hole, the differences become enormous. Let's imagine you're watching someone fall toward a black hole. They're in a spacesuit. You're far away, safe, watching through a powerful telescope. Maybe you're in a spaceship hovering at a safe distance. At first, the person falling looks normal. They're drifting toward the black hole, pulled by its gravity, moving faster and faster. As they get closer to the event horizon, you notice something strange. They're slowing down. Not just moving slower through space, everything about them is slowing down. Their arm movements become sluggish. They seem to be falling in slow motion. You keep watching, they get closer to the event horizon, and they slow down more and more. They're approaching the boundary, but they never seem to quite reach it. They get closer and closer, moving slower and slower, until they appear to almost freeze in place. At the same time, something else is happening. They're getting dimmer. The light coming from them is changing color, shifting toward red, redder and redder, dimmer and dimmer. Eventually, they fade away completely, not because they fell in, not from your perspective anyway, but because the light from them has been stretched so much, redshifted so dramatically that it's no longer visible, and time for them has appeared to slow so much that they look frozen, suspended forever at the edge. From your distant perspective, they never cross the event horizon. They approach it forever, but never quite reach it. But what about from their perspective? If you were the one falling, what would you experience? Everything would feel normal, completely, utterly normal. You'd be falling, sure, gaining speed, but your watch would tick along at the same rate it always has. Your thoughts would flow at normal speed. If you looked at your hands, they'd move normally. You'd look ahead and see the event horizon approaching, and you'd reach it, you'd cross it. There wouldn't be a flash of light or a feeling of passing through something. The event horizon isn't a thing you can touch. It's just a boundary in space-time, a point of no return. You might not even notice the exact moment you crossed it. But once you cross, there's no going back. Every direction you could move, every path through space-time available to you leads inward, toward the singularity at the center. You'd keep falling, time would continue for you, your watch would keep ticking. But if you could look back, if you could see the universe you left behind, you'd see something astonishing. The universe would be speeding up. Stars would move faster in their orbits. Time out, they would seem to flow quickly, like a time-lapse video. If you could see far enough into the future, you might watch stars burn out, new stars form, the universe aging rapidly before your eyes. This is the exact opposite of what the outside observer sees. They see you frozen, you see them accelerated. Both experiences are real. Your mind might be drifting now. That's good. That's what should happen. These ideas are strange, and it's okay if they feel dreamlike. It's okay if you're not holding onto every detail. The universe is strange. Time is stranger than we thought, and that's beautiful in a way. Why does this happen? Why does time slow down near a black hole? The answer has to do with how mass curves space-time. Remember the trampoline analogy, the bowling ball creating a dip. That dip isn't just in space, it's in time too. Actually, and this is fascinating, most of the curvature is in time, not space. When we think about gravity on Earth, we think about things falling down. We think about space being curved. But what's really happening is that time is flowing at different rates at different heights. Your head is slightly farther from Earth's center than your feet. Time flows slightly faster at your head than at your feet. The difference is impossibly small, unmeasurable in any practical sense, but it's there. Because of this tiny difference in time flow, the paths through space-time curve. Objects follow those curves. We call it falling. Gravity, at its core, is about time flowing at different rates. Near a black hole, this effect becomes extreme. The closer you get to all that concentrated mass, the more time slows, not just a little, not microseconds, dramatically. At the event horizon itself, from the perspective of someone far away, time appears to stop completely. This is why the outside observer never sees anything cross the horizon. To them, time at the horizon has frozen. An object approaching it would appear to take forever to reach it, literally forever. But for the object itself, time continues. It crosses, it falls in. Eventually, it reaches the singularity. Two different stories, both true, depending on where you're standing. The mathematics that describes this was worked out in 1916, just months after Einstein published his general theory of relativity. A physicist named Karl Schwarzschild solved Einstein's equations for a perfectly spherical mass. Schwarzschild was in the German army at the time, serving on the Russian front during World War I. In between his duties, he did physics. He found a solution that described spacetime around a point mass, what we now call a black hole. He found that there's a special radius. If you compress enough mass inside that radius, space-time curves so severely that nothing can escape. The radius depends on the mass. More mass means a bigger radius. For something with the mass of the Sun, that radius is about 3 kilometers. Compress the Sun down to a ball 6 kilometers across, and it becomes a black hole. For Earth, the radius would be about 9 millimeters. Compress Earth down to the size of a marble, and it would become a black hole. Schwarzschild's solution showed that these objects could exist mathematically, but for decades, physicists weren't sure if they could exist in reality. Maybe something would prevent them from forming. Then we found them. The first strong evidence came in 1964. Astronomers detected X-rays coming from a source in the constellation Cygnus. They called it Cygnus X1. When they looked more carefully, they saw a visible star there. A bright, massive star, but it was wobbling, moving in an orbit, orbiting around something invisible. By watching how the star moved, they could calculate the mass of the invisible object. It was too massive to be anything we knew about except a black hole. About 10 times the mass of the Sun, compressed into a region just a few kilometers across. It had to be a black hole. Since then, we've found many more. We've watched stars orbit the supermassive black hole at the center of our galaxy. We've detected gravitational waves from black holes colliding billions of light years away. In 2019, we took a picture, not of a black hole directly. You can't see a black hole by definition, but we photographed the shadow of a black hole surrounded by glowing gas. The black hole is in the center of a galaxy called M87, about 53 million light-years away. It's enormous, more than 6 billion times the mass of the Sun. The image shows a dark circle, the black hole's shadow, surrounded by a bright ring. That ring is gas, heated to billions of degrees as it swirls around the black hole before falling in. The gas is so hot it glows, emitting light we can detect. That image confirmed what the equations predicted. Black holes exist. They have event horizons. They warp spacetime just as Einstein said they would. And they warp time. You might be wondering, could we use this? Could we travel through time? The answer is, sort of. You could absolutely use a black hole to travel to the future. All you'd need to do is get close to one, hover there for a while, then leave. When you return to Earth, you'd find that more time had passed here than you experienced. You'd have effectively jumped forward in time. If you spent what felt like a year near the event horizon of a massive black hole, you might return to find that 1,000 years had passed on Earth. Everyone you knew would be long gone. Civilizations would have risen and fallen. You'd step out into a future you could hardly recognize. This is real. This would actually happen. It's not speculation. It's a consequence of time dilation, which we know is real. The only problem is practical. The nearest known black hole is about 1,000 light-years away. We'd need technology far beyond what we have to get there. And you'd need tremendous energy to hover near a black hole without falling in. But in principle, it's possible. Traveling to the past, though, that's much harder, maybe impossible. Black holes alone won't do it. You'd need something else, something exotic. A wormhole, perhaps, or some other structure in spacetime that we're not sure exists. For now, time travel to the past remains in the realm of theory and science fiction. But the future is waiting for anyone who can get close enough to a black hole and come back. Your body probably feels heavy now, relaxed. Maybe your thoughts are getting a bit fuzzy. That's perfect. We've covered a lot. The strangeness of time, how it flows differently in different places, how black holes curve spacetime so severely that time nearly stops at their edges. But there's more to the story, more beauty, more strangeness. We can think about it slowly, gently, there's no hurry. Inside the event horizon, something even stranger happens. Outside, space is space and time is time. You can move left or right, forward or back. You can't move backward in time, but you can stay still in space. Inside a black hole, the roles reverse. Moving toward the singularity becomes as inevitable as moving forward in time. You can't stop. You can't turn around. Every possible path through spacetime leads to the center. In a way, the singularity isn't a place in space. It's a moment in time, a moment in your future that you can't avoid, just like you can't avoid tomorrow. Outside the event horizon, you can choose whether to fall in or escape. Inside, you've already made that choice. All that's left is to experience the consequences. Physicists describe it like this. Inside a black hole, the direction toward the singularity becomes the time direction. It's no longer a place you could theoretically avoid by turning around. It's a when, not a where. You're falling toward a moment, not a location. What would happen to you as you fell? There's a term for it, spaghettification. It sounds funny, but the process itself wouldn't be pleasant. Remember, gravity gets stronger the closer you are to a mass. Your feet, being closer to the singularity than your head, would feel stronger gravity. The difference in gravitational pull between your head and your feet would stretch you out. For a small black hole, this stretching would be extreme. Long before you reach the event horizon, the difference would tear you apart. You'd be stretched into a long, thin strand, hence the name. For a supermassive black hole, though, the effect is much gentler. The event horizon is far from the singularity. The change in gravity across your body would be small, almost negligible. You could cross the event horizon without being harmed. You'd have time before the stretching became severe. How much time would depend on the black hole's size. But eventually, as you approached the singularity, the tidal forces would grow. Space itself would be stretched and squeezed, and you'd be stretched and squeezed with it. At some point, the stretching would overcome the forces holding your atoms together. You'd be pulled apart at the molecular level, then the atomic level. Eventually, all that would be left of you would be your fundamental particles, strung out in a line, falling into the singularity. What happens at the singularity itself? We don't know. Our equations break down there. They give us infinities, which usually means we're missing something. Maybe quantum mechanics prevents the singularity from being a true point. Maybe spacetime becomes something else, something we don't understand yet. Maybe the very question stops making sense. It's one of the great mysteries. But here's something comforting. You'd never have to worry about any of this. The nearest black hole is incredibly far away. You're here, safe, lying down, relaxed. Black holes are out there, doing their strange work on spacetime, curving it, warping it, slowing time to a crawl at their edges. But they're not a danger, they're just part of the universe, strange and beautiful and remote. In 2015, scientists detected something remarkable. Two black holes, each about 30 times the mass of the Sun, were orbiting each other. They'd been doing this for millions of years, gradually spiraling closer together. As they orbited, they created ripples in spacetime itself, gravitational waves. These waves spread outward at the speed of light, carrying energy away from the system. The black holes spiraled closer, faster, their orbit shrinking. Finally, they collided. In a fraction of a second, they merged into a single, larger black hole. In that brief moment, they released more energy than all the stars in the observable universe combined, not as light, as gravitational waves. Those waves traveled through space for 1.3 billion years. They passed through galaxies, through vast stretches of emptiness, growing weaker as they spread. On September 14, 2015, they passed through Earth. Scientists had built detectors specifically to catch these waves. 2 detectors, one in Louisiana and one in Washington State. Each detector is an L-shaped tunnel, each arm 4 kilometers long. When the gravitational wave passed through, it stretched and squeezed spacetime itself. One arm of the L got slightly longer, the other slightly shorter. Then they switched. The oscillation lasted less than a second. The change in length was incredibly tiny, far smaller than the width of an atomic nucleus, but the detectors were sensitive enough to measure it. That was the first direct detection of gravitational waves, proof that they exist, proof that black holes can collide, proof that spacetime itself can ripple and wave. Since then, scientists have detected dozens more. Each collision has a characteristic sound when the data is converted to audio. A chirp, starting low and rising in pitch, then cutting off suddenly. That chirp is the sound of two black holes spiraling together faster and faster, time dilating more and more until they merge. It's the sound of spacetime being shaken. Your eyes are probably closed now, you're breathing slow and steady. The ideas are washing over you like waves. That's how it should be. The universe is strange, stranger than we imagined. Time doesn't flow the same everywhere. Space and time are woven together. Mass curves them both. And out in the darkness, black holes sit, warping everything around them. Think about what this means for our understanding of time. We experience time as a straight line, past, present, future. 1 second follows another. We remember the past, but not the future. We move through time in one direction. But time isn't really a line. It's more like a dimension, similar to space. And just like space can be curved, time can be curved. Near a black hole, time curves so severely that it almost loops back on itself. The past and future become tangled in strange ways. Some solutions to Einstein's equations suggest that rotating black holes might create even stranger structures. Closed time-like curves, paths through spacetime that loop back to their starting point in time. If you followed one of these paths, you'd end up in your own past. Do these exist in real black holes? Probably not. Probably there are reasons they can't form. Quantum effects might prevent them, or they might require more exotic matter than exists in our universe. But the mathematics allows for them, and that's fascinating. It suggests that time is even stranger than we thought, not just flowing at different rates, but potentially able to loop, to curl back on itself. The universe might have structures we haven't dreamed of yet. There's something called the information paradox. Information in physics can't be destroyed. If you burn a book, the information in the book isn't lost. It's scrambled, turned into heat and ash and smoke, but in principle, with enough knowledge of every particle's position and motion, you could reconstruct the book. Information is conserved. But what happens when something falls into a black hole? From outside, we can never see it cross the horizon. From inside, it falls to the singularity, and then what? The information seems to be gone, destroyed. But information can't be destroyed. That's a fundamental principle of quantum mechanics. This is the paradox. General relativity says the information is lost. Quantum mechanics says it can't be. Both theories seem unshakable, but they contradict each other. Stephen Hawking worked on this problem for decades. He showed that black holes aren't completely black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. Over enormous timescales, this radiation causes black holes to evaporate. They shrink. Eventually, they disappear completely. Hawking initially thought the radiation was random, carrying no information about what fell in. But later work suggests the information might be encoded in the radiation in subtle ways. We still don't have a complete answer. It's one of the deepest questions in physics. Solving it might require a theory that unifies quantum mechanics and gravity, a theory we don't have yet. But we're working on it, thinking about it, trying to understand. You're drifting now, that's good, let yourself drift. The universe is full of mysteries. Black holes are just one of them. They sit out there, bending light, bending time, pulling matter into their depths. We've learned so much about them. We've photographed their shadows. We've heard them collide. We've measured how they warp spacetime. But there's still more to learn, more to discover. And that's okay. Mysteries are part of what makes the universe beautiful. Our own galaxy has a black hole at its center. Sagittarius A star, 4 million solar masses, sitting 26,000 light-years away. Scientists have been watching stars orbit it for years. One star, called S2, has an orbit that brings it very close. At its closest approach, it's only about 17 light hours from the event horizon. Still far, but close enough that time dilation becomes measurable. When S2 is at that closest point, its light shifts. The wavelengths stretch slightly. This is gravitational redshift, a consequence of time dilation. The star itself doesn't slow down from its own perspective, but light climbing out of the black hole's gravity well loses energy, shifts to longer wavelengths, appears redder. We can measure this. We can see time dilation happening in real time in our own galaxy. It's not just theory, it's observable, real. Sometimes people ask, what would it look like to orbit a black hole? If you were in a spaceship orbiting at a safe distance, what would you see? The black hole itself would be black, of course, a perfect circle of darkness against the stars, but around it, you'd see something extraordinary. Light from stars behind the black hole would be bent around it. Gravity lens effects would create multiple images of the same stars. The starlight would curve, following the warped spacetime, creating a ring of light around the dark circle. If there was gas or dust falling into the black hole, it would form an accretion disk. The gas would glow as it heated up from friction. It would orbit faster and faster as it got closer, eventually reaching a significant fraction of the speed of light. The disk would be bright, blindingly bright, different colors depending on temperature. The inner parts hotter might glow blue or white, farther out, cooler, glowing red. You'd see the disk both in front of the black hole and behind it, because light from the far side would be bent up and over the top, curving around to reach your eyes. The whole scene would look alien, distorted, light bending in ways it never does in flat spacetime. And if you watched long enough, if you could see individual particles of gas falling in, you'd see them slow down as they approached the event horizon. Freeze, fade away. You'd be watching time itself slow to a stop. You're very relaxed now. Your body feels heavy, sinking into whatever surface you're lying on. Your mind is quiet, just following along, or maybe drifting away entirely. That's perfect. That's exactly right. There's a thought experiment called the twin paradox. We touched on it earlier, but we can think about it more carefully. Two twins, same age. One stays on Earth. One gets on a spaceship and travels close to the speed of light. Not near a black hole this time, just moving very fast through flat spacetime. When the traveling twin returns, they've aged less than the one who stayed home. This is time dilation due to motion, not gravity, but the principle is the same. Time flows differently depending on your motion through spacetime. The twin who traveled feels like they only took a short trip, maybe a few years, but when they return, decades or centuries might have passed on Earth. They'd return to a world they don't recognize. Their twin would be ancient or dead. Society would have changed. Technology evolved. Everything familiar would be gone. They'd be a time traveler, but only forward, no way back to the time they left. This would actually happen. It's not fiction. The math is clear. The physics is solid. But no one has ever traveled fast enough for the effect to be noticeable. The fastest spacecraft we've built only reach a tiny fraction of light speed. The time dilation is real, but measured in nanoseconds, not years. Near a black hole, though, you don't need to move fast. You just need to be deep in the gravity well. The effect is the same. Time for you slows relative to someone far away. We can think about time in a different way now. Time isn't a river flowing at the same rate everywhere. It's more like a landscape, a terrain. In some places, time flows fast. In others, slow. The landscape is shaped by mass and energy. We live in a relatively flat part of this landscape. Time flows smoothly. We don't notice the small variations. But out there in the universe are deep valleys, black holes, places where the terrain of time drops steeply. If you ventured into one of those valleys, you'd find time flowing differently. Not wrong, not broken, just different. And if you came back, you'd have traveled through less time than the rest of the universe. It's strange, beautiful, unsettling maybe. But it's real. The universe has existed for about 13.8 billion years. At least, that's how long it's been from our perspective here on Earth. But from the perspective of a photon, a particle of light, no time has passed at all. Photons travel at the speed of light. At that speed, time doesn't pass. If a photon could think, it wouldn't experience any duration between being emitted and being absorbed. From its perspective, the journey is instantaneous, no matter how far it travels. Light from the Big Bang, light that's been traveling for 13.8 billion years, experienced zero time along the way. This is hard to wrap your mind around. Time is something we experience so fundamentally that imagining it not passing seems impossible. But that's the reality. At the speed of light, time stops. Black holes approach this strangeness in a different way, not by moving fast, but by warping spacetime so severely that time slows to a crawl. Same result, different cause. You might be wondering about what's inside a black hole, what actually happens there. The truth is, we don't know. We can't know, not directly. No information escapes from inside the event horizon. No light, no signals, nothing. Our best theory, general relativity, predicts a singularity at the center, a point where density becomes infinite and spacetime curvature becomes infinite. But physicists don't really believe in infinities in nature. Infinities usually mean our theory is breaking down, that we need a better theory. Quantum mechanics might save us. Maybe quantum effects prevent the singularity from forming. Maybe spacetime becomes quantum foam, a bubbling mess of probability and uncertainty. Or maybe something else happens, something we haven't thought of yet. The interior of a black hole might be the ultimate unknown, a place forever beyond our ability to observe. And there's something almost poetic about that, the universe keeping secrets, some things that will always be mysterious, no matter how much we learn. Your breathing is very slow now, deep, regular. You're right on the edge between waking and sleeping, or maybe you've already crossed over. Either way, it's fine, you're safe, comfortable, relaxed. The universe is out there, vast and strange. Black holes are bending time, light, space itself, but you're here, warm, at rest. We've come a long way from thinking about time as a simple, steady flow, from thinking about the universe as a stage where events happen, with time ticking along the same for everyone. Einstein showed us that time is flexible, relative, woven into space. Black holes take that flexibility to the extreme. They're not monsters, not destroyers. They're natural consequences of how gravity works. When enough mass gets compressed into a small enough space, spacetime curves so much that time almost stops. It's just physics, beautiful, strange physics. There's a black hole binary system called GW150914. That's the designation for the first gravitational wave detection. Two black holes spiraling together. As they orbited, they lost energy to gravitational waves. The orbit decayed. They moved closer. In the final moments, they were orbiting each other hundreds of times per second. Time dilation was extreme for both of them. Then they merged. The resulting black hole vibrated like a struck bell. Spacetime rang. The vibrations sent out more gravitational waves, the signature chirp we detected. All of this happened 1.3 billion years ago. The waves traveled all that time to reach us. When they passed through Earth, spacetime here rippled, just slightly, just enough to measure. We felt an echo of those black holes colliding. We felt spacetime shake. And embedded in those waves was information about time dilation, about how spacetime curves, about the physics of black holes. It's one of the most remarkable things humans have ever detected. You're drifting deeper now. Words are just sounds. Ideas are just gentle shapes in your mind. That's good. That's what should happen. Sometimes people ask if anything can escape a black hole. The answer is no, not from inside the event horizon. But black holes aren't completely black, not forever. Hawking radiation means they slowly evaporate, over timescales so long they're hard to imagine. A black hole with the mass of the Sun would take about 1067 years to evaporate. That's a 1 followed by 67 zeros. Far, far longer than the current age of the universe. Smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. But stellar mass black holes and supermassive black holes will be around for an inconceivably long time. Eventually, though they'll fade, the radiation will carry away their mass bit by bit. The event horizon will shrink. In the final moments, the black hole will be tiny, hot, radiating intensely, then it will vanish completely. A flash of light and it's gone. All that will remain is the radiation it emitted over its lifetime, spread out through the universe, carrying away energy, maybe information, we're not sure. Imagine watching a black hole evaporate. Of course, you'd need to be incredibly patient. It would take longer than the current age of the universe. But imagine you could somehow speed up time, watch the whole process in fast forward. At first, nothing seems to happen. The black hole just sits there, massive, dark, warping spacetime. Then very slowly it starts to shrink, not by much, just slightly. The shrinking accelerates, still slowly by human standards, but faster than before. As the black hole gets smaller, the evaporation speeds up. Smaller black holes emit more radiation. Eventually, it's small, tiny, radiating furiously. And then, in a final burst, it's gone. The warped spacetime heals, flattens out, returns to normal. As if the black hole was never there. But it was there for a long, long time. And during that time, it shaped the space around it, pulled in matter, emitted radiation, affected the orbits of stars. It was real, it existed, it mattered. And then it was gone, returned to energy, scattered into the universe. Everything is temporary, even black holes. Nothing lasts forever, everything changes, everything ends. But while things exist, they're real, they matter, they affect the world around them. And that's enough. Your mind is very quiet now. Thoughts come and go like clouds, drifting, dissolving. You're not holding onto anything, just letting it all flow past. There's a philosophical question about black holes. If you fell into one and experienced time normally from your own perspective, but appeared frozen from an outside perspective, which one is real? Did you fall in, or didn't you? The answer is both. Both are real. Both are valid descriptions of what happened. From your frame of reference, you fell in. You crossed the event horizon. You reached the singularity. From the outside frame of reference, you're frozen at the horizon forever. You never cross. Both stories are true. They're just told from different perspectives. This is one of the most profound insights of relativity. There's no absolute truth about events, no view from nowhere, no God's eye perspective. Only different frames of reference, different perspectives, all equally valid. Your truth and someone else's truth might be different, and both can be correct. This applies to more than just black holes. In life, people experience things differently. Their perspective is shaped by where they are, what they've experienced, how they move through the world. What's true for them might not be true for you, and vice versa. That doesn't mean one of you is wrong. It means truth is perspective dependent. Near a black hole, this becomes literal, physical, measurable. But maybe it's always been true in a deeper sense. Maybe we've always been looking at reality from our own unique perspective, our own frame of reference. And maybe that's okay. Maybe that's how it's supposed to be. You're barely aware now. The words are just sounds, rhythm, cadence. The meaning is secondary or gone completely. That's good. In the depths of space, far from any star, it's dark. Not just dark, completely black, no light at all. But it's not empty. Space is never truly empty. There are fields, quantum fluctuations, virtual particles appearing and disappearing. Even in the darkest void, something is happening. Near a black hole, these quantum fluctuations become important. Right at the event horizon, pairs of particles can appear. One falls into the black hole, the other escapes. From a distance, it looks like the black hole is radiating, emitting particles. This is Hawking radiation, named after Stephen Hawking, who first predicted it. It's a quantum effect, happening at the boundary between inside and outside. The black hole doesn't create these particles. They come from the quantum vacuum, from the underlying structure of spacetime itself. But the black hole's presence makes them real, makes them observable. And slowly, over incomprehensible timescales, this radiation carries away the black hole's mass. Until eventually, there's nothing left. Even nothing is something in quantum mechanics. The vacuum isn't empty, it's full of potential, full of possibility. Particles and antiparticles flickering in and out of existence, too fast to see, too brief to measure. But real nonetheless. This is the universe at its smallest scale, the quantum scale, where things are uncertain, probabilistic, fuzzy, where particles don't have definite positions until you measure them, where they can be in multiple places at once. It's strange, counterintuitive, deeply weird. But it's how reality works at the smallest scales. Black holes sit at the intersection of two theories: general relativity, which describes gravity and spacetime on large scales, and quantum mechanics, which describes particles and fields on small scales. These two theories don't quite fit together. They predict different things in extreme conditions. Inside a black hole, both should be important, but we don't have a theory that unifies them. This is one of the great unsolved problems in physics. Quantum gravity, a theory that describes how gravity works at quantum scales. We have ideas, string theory, loop quantum gravity, other approaches. But we don't have a complete, tested theory yet. The interior of a black hole might be where quantum gravity matters most. Near the singularity, both spacetime curvature and quantum effects become extreme. Our current theories break down, give us infinities, nonsense. The real answer must be something we haven't figured out yet. And that's okay, we don't have all the answers. Science is a process, an ongoing conversation with nature. We ask questions, we test ideas, we learn. Sometimes we discover new things. Sometimes we realize our old ideas were wrong. But we keep going, keep questioning, keep exploring. Black holes are part of that exploration. They're laboratories for extreme physics, places where our theories are pushed to their limits. By studying them, we learn about gravity, about spacetime, about the fundamental nature of reality. Your breathing is a whisper now. In, out. Barely moving. Your body at complete rest. We've come so far in understanding black holes. From Einstein's equations in 1915 to the first image in 2019. A century of work, thousands of scientists, countless hours of observation and calculation. And we've learned so much. We know black holes exist. We know they warp spacetime. We know they affect time and light. We've measured them, photographed them, heard them collide. But there's still more to learn, always more to learn. The universe is deep, complex, full of subtlety and nuance. Every answer raises new questions. Every discovery opens new avenues of inquiry. That's what makes science beautiful. It's never finished, never complete. There's always another mystery, another puzzle, another horizon to explore. Black holes are one of those horizons, literally. The event horizon is a boundary we can't cross and return from, a limit to what we can observe. But that doesn't stop us from trying to understand, from pushing the boundaries of knowledge. From wondering what's beyond. You're beyond conscious thought now, drifting in the space between waking and sleeping. Or already asleep, it's hard to tell. The universe is full of boundaries. The speed of light, a boundary we can't cross. The event horizon, a boundary we can't return from. The Planck length, the smallest meaningful distance. The age of the universe, the farthest back we can see. These boundaries define the limits of what's possible, what's knowable. But they also inspire us to push further, to see what we can learn even within those limits. To map out reality as far as we can reach. And we've reached far, farther than anyone thought possible a century ago. We've seen the universe as it was billions of years ago. We've detected gravitational waves from cosmic collisions. We've photographed the shadow of a black hole. We've done impossible things. And there's more to come, more discoveries, more revelations. The universe will keep surprising us, keep showing us new wonders. As long as we keep looking, keep asking questions, keep exploring. But for now, rest. Let the universe be, let the mysteries wait. There's time for exploration later, time for wonder later. Right now, there's only rest. Only sleep. Only the quiet darkness. Sometimes people ask if anything can escape a black hole. The answer is no, not from inside the event horizon. But black holes aren't completely black, not forever. Hawking radiation means they slowly evaporate, over timescales so long they're hard to imagine. A black hole with the mass of the Sun would take about 1067 years to evaporate. That's a 1 followed by 67 zeros. Far, far longer than the current age of the universe. Smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. But stellar mass black holes and supermassive black holes will be around for an inconceivably long time. Eventually, though, they'll fade. The radiation will carry away their mass bit by bit. The event horizon will shrink. In the final moments, the black hole will be tiny, hot, radiating intensely, then it will vanish completely. A flash of light, and it's gone. All that will remain is the radiation it emitted over its lifetime, spread out through the universe, carrying away energy, maybe information, we're not sure. The universe will outlast us. It will outlast our sun. It will outlast the stars. Trillions of years from now, the last stars will die. The universe will be dark, cold, empty, except for the slowly evaporating black holes. And eventually, even they will be gone. What then? We don't know. Maybe nothing. Maybe the universe becomes a thin soup of particles, spread so far apart they'll never interact. Maybe something we can't predict will happen. But that's so far in the future, it's almost meaningless to us. For now, the universe is full of light, full of stars and galaxies and planets, full of mysteries and beauty. And we're here trying to understand it, piece by piece. You're barely aware of words now, just the sound of a voice, distant, like it's coming from another room. Your body is completely relaxed, heavy, still. Your mind is quiet. This is rest, deep rest. Black holes teach us that the universe is stranger than common sense suggests, that time isn't what we thought it was, that space and time are connected, flexible, curved by mass. They teach us humility. There are limits to what we can know, places we can never visit, not even in principle, information we can never recover. But they also teach us wonder. The universe follows rules, mathematical rules, elegant rules, and those rules allow for structures as bizarre as black holes. We can understand them, even if we can never touch them. We can write equations that describe them. We can detect their effects from billions of light years away. We can photograph their shadows. We can know them in a way. And that's remarkable. Time is flowing right now, for you, for me, for everyone and everything. On Earth, time flows at one rate, on GPS satellites slightly faster, near the sun slightly slower. And out there, near black holes, time slows to almost nothing. All of these are true simultaneously. All of these are real. Time is relative, personal, dependent on where you are and how you're moving. There's no universal now, no absolute present moment shared across the universe. Just countless perspectives, each experiencing their own flow of time. It's strange to think about, almost unsettling. But it's beautiful too. Your thoughts are probably fragments now, images, feelings, nothing coherent. That's perfect. You don't need to understand everything. You don't need to remember it all. Just let it wash over you. Let yourself rest. In the darkness of space, black holes wait. They've been there for millions or billions of years. They'll be there for trillions more. Silent, patient, warping the fabric of reality around them. Light bends near them, time slows, space curves. But from their perspective, if they could have a perspective, everything is still, quiet, timeless. They exist in their own reality, separate from ours. And we exist in ours, observing them from afar, measuring their effects, trying to understand. The universe is vast, bigger than we can really comprehend, billions of galaxies, each with billions of stars. And scattered throughout, millions or billions of black holes. Each one a place where time behaves strangely, where the rules are different. We live in a gentler part of the universe, where time flows smoothly, where space-time is relatively flat. And that's good, that's where life can exist, where thoughts can form, where we can wonder about the cosmos. You're on the edge of sleep now, or past it. Words are just sounds in the darkness. Gentle, calm, rhythmic. Time flows differently everywhere, but here now for you, it's flowing gently. Seconds passing, minutes passing. Each moment drifting into the next. No urgency, no rush. Just time flowing naturally. Black holes are far away. You're here. Safe. Warm. Resting. The universe continues. Stars shine, planets orbit, black holes curve space-time. But for you, right now, there's just this moment. This quiet. This rest. Time is strange and beautiful. Space is curved. And you are drifting. Drifting gently. Into sleep. Into peace. Rest now. Let go. Time will take care of itself. You don't need to think about it. You don't need to do anything. Just rest. The universe is out there. Vast, ancient, strange. Full of wonders. But right now, the only thing that matters is your breathing. Slow, deep, easy. In and out. In and out. Time slows near a black hole. And here, now, in this moment, time slows for you too. Not because of gravity. Because of rest. Because of sleep. Let yourself drift. Let yourself fall. Not into a black hole. Into sleep. Into dreams. Into the quiet darkness. You're safe. You're warm. You're at rest. And time flows on. Gently. Quietly. Carrying you into sleep. Sometimes at night, when you can't sleep, you might find yourself thinking about time. How it keeps moving, how you can't slow it down or speed it up, how yesterday is gone and tomorrow hasn't arrived yet. There's something both comforting and unsettling about time's relentlessness. But what we've been talking about changes all of that. Time isn't relentless everywhere. It's not the same for everyone. Near a black hole, time becomes almost negotiable. Not by you, you can't control it, but it flows differently depending on where you are. And that changes everything. Think about getting older. We all do it. Every second that passes, we're a second older. Time marches forward and we march with it. But what if you could slow that down? Not by stopping aging biologically, but by literally experiencing less time. Near a black hole, you would age more slowly than someone far away, not because your cells work differently, but because less time actually passes for you. 1 year for you could be 10 years for them, or 100, or 1,000. You'd return younger than people who were born after you left. It's not quite immortality, you'd still age, time would still pass for you. But you'd move through less of it compared to everyone else. There's something profound about that. It means time isn't this external thing forcing us all forward at the same rate. It's personal, intimate, part of your individual journey through the universe. Your time is yours, different from everyone else's. Your breathing has settled into a deep rhythm now. In, out, each breath slower than the last. Your body knows how to rest. We measure our lives in time. Years, days, hours, minutes. We organize everything around time when we wake up, when we work, when we eat, when we sleep. Time structures our existence. But that structure is local, earthbound, human scale. In the larger universe, time is much more flexible, more personal, more strange. A clock on a GPS satellite ticks faster than a clock on the ground, not by much, tiny fractions of a second per day. But it's real, measurable. The satellites have to correct for it constantly. If they didn't, GPS wouldn't work. Your phone couldn't tell you where you are. This isn't abstract physics happening in some distant part of the universe. It's happening right now, above your head, affecting technology you use every day. Time dilation is real. It's happening all around us. We just don't usually notice because the effects are small at our scale. But near a black hole, the effects become impossible to ignore. Let your mind wander for a moment. Imagine you're floating in space, not near a black hole, just in the vast emptiness between stars. No gravity pulling on you, no massive objects nearby, space-time around you is flat, uncurved. Time flows smoothly, your watch ticks at a steady rate. Now imagine moving closer to a massive object, a planet, then a star, then a black hole. As you get closer, space-time curves more and more. And your watch starts ticking more slowly compared to someone who stayed behind. Not from your perspective. To you, it still ticks once per second. But compared to that distant observer, you're moving through time more slowly. It's like descending into a valley. At the top, on flat ground, time flows at one rate. As you go deeper, time flows more slowly. At the bottom, near the black hole, time almost stops. But you don't feel yourself slowing down, you feel normal. It's only when you compare yourself to someone at the top that the difference appears. There's a kind of loneliness to that, isn't there? If you went to the bottom of that valley and stayed there, everyone you knew at the top would age rapidly. Their lives would speed past. By the time you climbed back up, they might all be gone. You'd return to a world that had moved on without you. But maybe there's beauty in it too. Time is relative, personal, your experience is your own. You can't share time with anyone, not really. Even here on Earth, even standing next to someone, you're experiencing slightly different time flows. The difference is immeasurably small, but it's there. We are all on our own journeys through space-time, connected but separate. Your mind is getting quieter now. Thoughts are slower, hazier. That's good, that's natural. You're letting go. Black holes teach us something about impermanence. Everything changes. Stars are born, they burn, they die. Planets form, they evolve. Eventually they're destroyed. Even atoms aren't permanent. Given enough time, they decay. But the rules stay the same. The laws of physics don't change. Einstein's equations, worked out more than a century ago, still describe reality perfectly. Black holes obey those equations. Time dilation follows those equations. There's something reassuring about that consistency. The universe is comprehensible, predictable, even if it's strange. We can write equations that describe how black holes work, how time dilates, how space curves. We can make predictions and test them. And when we test them, they're right. The universe follows rules, deep mathematical rules. We didn't invent those rules, we discovered them. They were always there, operating whether we knew about them or not. There's something peaceful about how predictable black holes are. Despite all their strangeness, despite warping time and space, they follow rules, precise mathematical rules. If you know a black hole's mass, you can calculate its event horizon. You can predict how much time will dilate at any distance. You can work out exactly how light will bend around it. The mathematics is complex, but it's exact. This is one of the beautiful things about physics. The universe might be strange, but it's not random. It follows patterns, laws, equations we can write down and solve. Black holes, for all their mystery, obey those laws perfectly. Your mind is very quiet now. Thoughts come and go like clouds. That's natural. That's good. Think about what it means that time is relative. It means there's no universal clock, no absolute timeline running through the universe. If you could somehow speak to someone near a black hole's event horizon and they said, "I've been here for an hour," they'd be telling the truth. Their watch would show 1 hour. They'd have experienced 1 hour. But from your perspective, decades might have passed. Both of you would be right. This isn't a trick or an illusion. It's the fundamental nature of time. Time is what you measure with a clock, and clocks in different places tick at different rates. There's no real time that's more correct than the others. All of them are equally valid. We like to think there's a universal now, a present moment that everyone shares, but that's not how the universe works. Your now is different from someone else's now if you're moving relative to each other, or if you're in different gravitational fields. The difference is usually tiny, unmeasurable in ordinary life, but it's there. And near a black hole, the difference becomes enormous. This has strange implications. Imagine 2 events happening in the universe, one near a black hole, one far away. Which happened first? The answer depends on who you ask. From one perspective, event A happened before event B. From another perspective, B happened before A. Both perspectives are correct. There's no absolute ordering of events in the universe, no universal timeline. Just different reference frames, each with its own version of when things happened. This challenges our intuition deeply. We feel like there should be a right answer, a true sequence of events. But the universe doesn't work that way. Time is relative, order is relative, even simultaneity is relative. 2 events that seem to happen at the same time to one observer might happen at different times to another. Both are correct. Your eyes might be closed now or open but unfocused. Either way, it doesn't matter. You're drifting, that's good. There's a thought experiment, Einstein's thought experiment. Imagine you're on a train moving very fast, near the speed of light. Lightning strikes both ends of the train simultaneously, front and back. To someone standing on the platform, watching the train pass, both strikes happen at exactly the same moment. But to you, on the train, the strike at the front happens first, then the strike at the back. Same 2 events, different orders depending on your motion. Both observers are right. This isn't about perception or signal delay. It's about the fundamental nature of time. There is no absolute simultaneity. Events that are simultaneous in one frame aren't in another. Near a black hole, this becomes extreme. An event that takes a second near the event horizon might take decades from the perspective of a distant observer. Not because signals are slow, but because time itself flows differently. Think about what this means for cause and effect. We're used to thinking cause comes before effect. Always, that's how time works. And it's true mostly. Within a single reference frame, cause does come before effect. But when you compare different reference frames, things get murky. For events that are very far apart in space, or in very different gravitational fields, the order can be ambiguous. Cause and effect become frame-dependent. This is deep, heavy, strange. But you don't need to figure it all out tonight. You don't need to solve the mysteries of time. You just need to rest, to let these ideas wash over you, to drift in the strangeness of it all. Your breathing is very slow now. Each breath takes a long time. In pause, out pause. The pauses are getting longer. Your body is settling deeper into rest. Black holes are patient. They've existed for billions of years. They'll exist for trillions more. They don't rush, they don't hurry. They just are. Sitting in space, warping time, existing. There's something we can learn from that patience. In our lives, we rush. We're always hurrying, trying to get things done, trying to save time. But time can't be saved. It just flows, at whatever rate it flows for you. And rushing doesn't create more time. It just makes the time you have feel more frantic. Maybe we could learn to be more like black holes, patient, present, just existing in our own flow of time. Not that black holes have consciousness, they don't, they're just objects, physical phenomena. But there's still something meditative about how they exist, how they simply are, without effort or struggle. You're on the edge of sleep now, teetering between awareness and unconsciousness. Sometimes you hear the words, sometimes they fade into background noise. Both are fine. Light from distant galaxies has been traveling for billions of years. It started its journey long before Earth existed, before the sun formed, before our galaxy looked anything like it does now. And it's still traveling, crossing the vast emptiness of space, moving at the speed of light. But from the photon's perspective, no time has passed. The journey is instantaneous, emitted and absorbed in the same moment from its frame of reference. This is what happens at the speed of light. Time stops. Not slows down, stops completely. If you could travel at the speed of light, which you can't because you have mass, you wouldn't experience any time passing. The entire journey, no matter how far, would take zero time from your perspective. Black holes approach this strangeness in a different way. Not by moving at the speed of light, but by warping time so severely that it slows to a stop. Same result, different mechanism. Time can stop, or nearly stop, it's possible. We just don't experience it in our ordinary lives because we're not moving fast enough or deep enough in a gravity well. But it's real, happening out there in the universe. Time stopping or nearly stopping, while elsewhere time flows normally. All part of the same reality, all part of how space-time works. Your mind is barely holding on to these concepts now. They're slipping away, becoming dreamlike. That's perfect. You don't need to grasp them, you don't need to remember them. Just let them be. In the far future, trillions of years from now, the universe will be very different. All the stars will have burned out, the galaxies will have drifted far apart, space will be dark, cold, empty. Except for the black holes. They'll still be there, slowly evaporating, but still there. The last structures in the universe, the last remnants of when things were bright and hot and full of energy. Eventually, even they'll evaporate completely, turn to radiation, disappear. And then what? Just an empty universe, expanding forever, getting colder and more diffuse until there's nothing left but a thin soup of particles spread across unimaginable distances. Heat death, the end of everything. But that's so far away, it's almost meaningless. Trillions upon trillions of years. For now, the universe is full of light, full of structure, full of possibilities. We are here in the bright early days of the cosmos, when stars still shine, when galaxies still collide, when black holes are young and active. And you're here, now, in this moment. Breathing, existing, resting. Connected to all of it, part of the same universe that contains black holes and stars and vast stretches of empty space. You're made of atoms that were forged in stars. Carbon, oxygen, nitrogen, all the elements that make you up. They were created in stellar cores, released when stars died, scattered into space. Eventually, they came together to form you. You're stardust, literally. And someday, those atoms will return to the universe, scattered again. Nothing is lost, just transformed. There's a cycle to things. Stars form from clouds of gas. They burn, they die, they release their material, new stars form. Over and over, cycles within cycles. Black holes are part of this cycle too. They consume matter, slowly release it as radiation. Everything is connected, everything flows. Your breathing is barely there now. So slow, so quiet. Each breath is an event, spaced far apart in time. Time is strange near a black hole. But time is strange everywhere when you think about it. It flows always forward, never backward, at a rate that depends on gravity and motion. We experience it, we are embedded in it, we can't step outside it. Unless you're a photon, or at a black hole's event horizon. Then time stops, or nearly stops. Then you're outside the normal flow. But you're not a photon, and you're not at a black hole. You're here safe, warm, resting. Time is flowing for you at a normal, comfortable rate. 1 second per second, one moment following another. Nothing strange, nothing extreme. Just the gentle, steady flow of time carrying you through the night. We like to think there's a universal now, a present moment that everyone shares, but that's not how the universe works. Your now is different from someone else's now if you're moving relative to each other, or if you're in different gravitational fields. The difference is usually tiny, unmeasurable in ordinary life, but it's there. And near a black hole, the difference becomes enormous. You're breathing so slowly now. Each breath takes a long time. In and out. In and out. The rhythm is gentle, steady. Your body knows what to do. There's a kind of meditation in thinking about the universe this way. We spend so much of our lives rushing, worrying about time, trying to save time, trying to manage time. But time isn't really something we can control. It flows at the rate it flows. For us, here on Earth, that rate is fairly constant. But we could imagine a different life, a life near a black hole, where time flows differently. Would that life be slower, not from the perspective of the person living it? To them, seconds would still feel like seconds. But from our perspective, watching from far away, their life would be in slow motion. They could live what felt to them like a full life, decades of experience, but to us, it might only appear as a few years. Or the reverse, they could spend what felt like a few hours somewhere and return to find their whole world aged beyond recognition. Time is strange like that. There's comfort in the vastness of the universe. Problems that seem overwhelming to us are tiny on a cosmic scale. The universe doesn't care about our deadlines or our schedules. It just exists, vast, ancient, indifferent. Black holes don't worry, they don't rush, they just are. And maybe there's something we can learn from that, from the patience of cosmic time. You're very close to sleep now, or maybe already there. Your consciousness is flickering, fading. That's perfect. Scientists sometimes talk about the lifetime of black holes. Even though black holes can exist for trillions of years, they're not immortal. Eventually, through Hawking radiation, they evaporate. The process is slow, beyond imagination for any black hole we know about. But imagine watching one evaporate, time-lapse style. At first, nothing seems to happen. The black hole just sits there for billions of years, trillions of years. Its mass decreases, but so slowly you wouldn't notice. Then, as it gets smaller, the evaporation speeds up. Smaller black holes evaporate faster. In the final moments, the black hole is tiny, radiating energy furiously. And then it's gone. A flash, and then nothing. All that mass, all that warped spacetime, returned to energy and radiation. The event horizon collapses, spacetime heals, time flows normally again in that spot. It's like the black hole was never there. But of course, it was there for a long, long time. And anything that fell in during that time, where did it go? This is part of the information paradox. If the black hole evaporates completely and the radiation carries no information about what fell in, then that information is lost. But quantum mechanics says information can't be lost. Maybe the answer is that the radiation does carry information, encoded in subtle correlations between particles. Maybe there's a way to extract information from Hawking radiation if we knew how to look. Or maybe our understanding of information is incomplete. These are deep questions, questions that touch on the very foundations of physics. We don't have answers yet, but we're thinking about them, working on them, trying to understand. Your body is completely still now. Muscles relaxed. Breathing slow. Mind quiet. Let's think about something gentle for a while. The light from stars. Stars emit light. That light travels through space. Sometimes it passes near a black hole. When it does, the light's path curves. It follows the curved spacetime. From Earth, we can see this. If a star is directly behind a black hole from our perspective, we don't see the star go dark. Instead, we see the star's light bent around the black hole, creating a ring of light. Einstein predicted this in 1915. He called it gravitational lensing. It was first observed during a solar eclipse in 1919. Light from stars behind the sun was bent around the sun, making the stars appear in slightly different positions. This confirmed Einstein's theory. Gravity does bend light, space is curved. Black holes create much more extreme lensing. They can create multiple images of the same star, rings of light, arcs. It's beautiful in a way, light following the curves in spacetime, creating patterns. There's something almost alive about how light behaves. It always takes the fastest path through spacetime, not the shortest path through space, but the fastest path through spacetime. In curved spacetime, the fastest path is curved. Light doesn't know it's following a curve. It's not being pulled or pushed. It's just traveling in a straight line, but spacetime itself is curved, so the line curves too. It's elegant, simple in concept, complex in mathematics. Your breathing is almost imperceptible now. Slow, soft, quiet. You're resting deeply. Black holes come in different sizes, as we've talked about. The smallest we know of are a few times the mass of the sun. These formed from dying stars. There are probably millions of them in our galaxy alone. Then there are intermediate mass black holes, hundreds or thousands of times the sun's mass. We're not sure how these form, maybe from multiple smaller black holes merging, maybe from the collapse of giant clouds of gas. And then the supermassive black holes, millions or billions of times the sun's mass. Almost every large galaxy has one at its center. How did these form? We're not entirely sure. They might have started as smaller black holes that grew by consuming gas and stars, or they might have formed early in the universe's history from the direct collapse of massive clouds. Either way, they're ancient, as old as the galaxies themselves. Our galaxy's black hole, Sagittarius A star, has been there for billions of years. long before Earth formed, long before the Sun existed. It's been sitting at the center of the Milky Way, quietly warping spacetime, while generations of stars were born and died around it. There's a kind of permanence to black holes. Stars burn out, planets erode, even atoms can decay. But black holes just exist, patient, unchanging on human timescales. They'll be there long after we're gone, long after our sun dies, long after the Earth is dust. Warping time, bending space. Silent monuments to the strangeness of gravity. You're drifting in and out now. Awareness comes and goes. Sometimes you hear the words, sometimes they're just background noise. Both are fine. In 2020, scientists won the Nobel Prize for their work on black holes. One of them, Roger Penrose, proved mathematically that black holes are a natural consequence of Einstein's equations, that they will form under realistic conditions. The others, Reinhard Genzel and Andrea Ghez, led teams that tracked stars orbiting Sagittarius A star. Their observations proved that there's a supermassive black hole at our galaxy's center. Decades of patient work, tracking individual stars year after year as they orbited the invisible mass. One star, S2, orbits every 16 years. At its closest approach, it's moving at about 3% of the speed of light. That's about 5,000 miles per second. At those speeds, time dilation becomes measurable, not huge, but measurable. And they measured it. They saw S2's light shift in exactly the way Einstein's equations predict. It's one thing to have equations, it's another to see them confirmed in nature. That's what science does. It makes predictions, then checks them. And again, when we check Einstein's predictions about gravity and time, they're right. Your mind is barely tethered to consciousness now. Floating, drifting, almost gone. Imagine the first moments after a black hole forms. A massive star has collapsed. The core has fallen inward, compressed beyond the point of no return. An event horizon forms, a boundary in spacetime. For an outside observer, the collapsing matter appears to freeze at the event horizon. Time dilation is extreme. The star seems to fade away. But from the matter's perspective, it keeps falling through the event horizon toward the singularity. The black hole has formed. Spacetime around it is warped into a new shape. Gravitational waves ripple outward. Spacetime itself rings like a bell, settling into its new configuration. And then, stillness. The black hole just sits there, existing, warping spacetime, waiting. Waiting for something to fall in, or not, it doesn't matter to the black hole. It just is. There's something almost zen about black holes. They're not actively doing anything. They're not reaching out and grabbing things. They're just massive, and mass curves spacetime, and objects follow the curves. If you stay far enough away, you're safe. You can orbit forever. Only if you get too close, if you cross the event horizon, are you trapped. And even then, the black hole isn't doing anything to you. You're just following geodesics, the straightest paths through curved spacetime. It's geometry, not force. Your breathing has slowed to almost nothing. Each breath is long, so long. In, hold, out, hold. In, hold, out, hold. Your body is resting deeply. We've learned so much about black holes in the past century. From Einstein's initial equations in 1915 to Schwarzschild's solution in 1916 to the first detection in the 1960s to gravitational waves in 2015 to the first image in 2019. Each step has revealed more. And each step has confirmed that Einstein was right. Time and space are connected. Mass curves them, and the curvature creates what we experience as gravity. It's a complete rethinking of what gravity is, not a force, but a consequence of geometry. And black holes are where that geometry becomes extreme. Sometimes people ask, what would happen if a black hole suddenly appeared near Earth? The answer is, it depends on how close. If it appeared, say, where the moon is, we'd be in trouble. We'd be pulled toward it. The tides would be extreme. Earth would likely be torn apart. But if it appeared a few light years away, we probably wouldn't notice for a long time. Its gravity would affect us, but only slightly. We might see stars moving differently in that direction. We might notice light being bent. Eventually, over millions of years, it might affect the orbits of stars in our region of the galaxy. But there'd be no immediate catastrophe, no sudden destruction. Black holes are only dangerous if you get close. The nearest known black hole is about 1,000 light years away. That's incredibly far. Light takes 1,000 years to travel that distance. Even if it started moving toward us at high speed, we'd have plenty of warning, plenty of time to do whatever we could do, which realistically wouldn't be much. But it's not moving toward us, it's just sitting there wherever it is, orbiting the galaxy, minding its own business. You're asleep now, probably, or so close it doesn't matter. Your consciousness is a dim flicker, almost extinguished. That's good. In dreams, time does strange things. You might dream an entire lifetime in a single night, or experience hours in what's actually just minutes. Dream time doesn't match waking time. In a way, that's similar to time dilation. Different experiences of time, all equally real from the perspective of the person experiencing them. When you dream, you're in your own bubble of time, your own reference frame. Just like someone near a black hole is in their own reference frame, experiencing time their own way. Time is personal. We share a common time here on Earth because we're all in similar conditions, similar gravity, similar motion. But that's local, temporary. In the grand scheme of the universe, there's no shared time, just countless individual flows of time, each relative to the observer. Your dreams are forming now. Images, sensations, disconnected from waking logic. The mind does its own work while you sleep. Processing, consolidating, creating. Black holes will outlast everything we know. Stars will die, galaxies will drift apart, the universe will expand and cool. But black holes will remain for trillions of years, slowly evaporating, growing smaller. But still there, patient, timeless. There's something comforting about that. Not because black holes are friendly, they're not, they're just objects, physical phenomena. But because they're permanent in a way nothing else is. They'll be there long after we're gone, long after everything we've built is dust. Warping time, bending space. Existing. You're breathing so softly now, barely moving at all. Deep in sleep, or just about to cross that threshold. The event horizon is a threshold too. Not between waking and sleeping. Between escape and no escape. Between outside and inside. But unlike sleep, there's no waking up from crossing an event horizon. Once you're in, you're in. Time carries you forward, inevitably, toward the singularity. There's a finality to it. But we're not near any black holes. We are safe, distant, protected by the vastness of space. We can think about them, study them, wonder about them. But we don't have to fear them. They're part of the universe, strange and beautiful. But far, far away. Your mind is almost completely quiet now. Just a whisper of awareness. The words are sounds, rhythms. Nothing more. Einstein once said that time is an illusion. What he meant was that the separation between past, present, and future is not as absolute as it seems. In spacetime, all moments exist together. Past, present, future, all laid out in four-dimensional geometry. We experience them sequentially because we're moving through time, but from a broader perspective, they're all there, all part of the structure. Black holes teach us this. They show us that time is flexible, that present for one person is past or future for another. Time is not an absolute backdrop, it's part of the fabric of reality, and that fabric can bend. This is heavy stuff, deep stuff. But you don't need to understand it all. You don't need to remember it. Just let it be. Let the strangeness wash over you. Let yourself rest in the mystery. The universe is mysterious, full of things we don't fully understand. Black holes are just one example. Dark matter, dark energy, the quantum nature of reality, consciousness itself. All mysteries. But that's okay. We don't need to have all the answers. We can wonder, question, explore, and rest in the not knowing. You're resting now. Deeply. Completely. Time is flowing. For you, for everyone, for everything. But right now, time doesn't matter. There's no schedule, no deadline, no pressure. Just this moment, and the next, and the next. Each one flowing into the other. Gently, naturally. Black holes remind us that the universe is bigger than us, stranger than us, operating on scales we can barely imagine. Timescales of billions of years, distances of thousands of light years, masses of millions of suns. We are tiny in comparison, brief, fragile. But we are part of it all, made of the same stuff, following the same laws. Connected to the cosmos in ways we're only beginning to understand. Your breathing is barely there. A whisper of air, in and out. Your body is still. Your mind is still. Somewhere out there, a black hole is consuming a star. The star got too close, crossed the tidal radius. The gravity difference between one side and the other became too much. The star stretched, elongated, tore apart. Now it's a stream of gas, spiraling into the black hole. The gas heats up from friction, glows, emits X-rays. Telescopes can detect this. We've seen it happen. We call it a tidal disruption event. The star is gone, destroyed. Its atoms scattered into the accretion disk, slowly falling into the event horizon. From the star's perspective, if it could have won, time probably felt normal until the very end, until the tidal forces ripped it apart. From our perspective, watching from far away, the process looked slow, the gas appearing to freeze as it approached the horizon. Two perspectives, both real. Death is a kind of crossing, isn't it? A threshold. We don't know what's on the other side, if anything. Maybe it's like crossing an event horizon, a point of no return. Or maybe it's just nothing, an ending, consciousness extinguished. We don't know. But there's something peaceful about not knowing, about accepting the mystery. You're almost completely asleep now. Just a tiny thread of awareness left. Soon even that will fade. And you'll be fully in the world of dreams. Or in the deep, dreamless darkness. Either way, you'll be at rest. The universe doesn't require us to understand it. It just is. Black holes warp time, whether we comprehend them or not. Stars shine, whether we see them or not. The cosmos unfolds according to its laws, indifferent to our knowledge or ignorance. And there's something freeing about that. We can let go of the need to understand everything. We can rest in wonder instead. Time near a black hole slows to almost nothing. And here now, in this quiet space, time has slowed for you too. Not from gravity, from rest, from letting go, from surrender to sleep. There's a word, timelessness. The feeling of being outside time, of time not mattering. Near a black hole's event horizon, time almost stops. In deep sleep, we lose track of time. Both are kinds of timelessness, different but similar in effect. You're timeless now, floating in the space between waking and sleeping, between awareness and unconsciousness. It's peaceful there, safe, quiet. The universe has existed for nearly 14 billion years. It will exist for far longer, trillions of years, maybe forever. We're here for an eye blink, a fraction of cosmic time. Our lives are brief, so brief, but they're ours, real, meaningful. Even if the universe doesn't notice, even if we're forgotten. We existed, we wondered, we reached out to understand. That matters. Your thoughts are dissolving now. Not quite thoughts anymore, just feelings, impressions. The boundary between self and not self blurring. This is what sleep does. It dissolves the boundaries. You become less distinct, less defined. You merge with the darkness, with the quiet. In the darkness of space, a black hole waits. No eyes to see it, no ears to hear it. Just gravity, pulling, warping, bending. Silent, patient, eternal. And here, in the darkness of your room, you wait too. For sleep to take you fully. For consciousness to fade. For dreams to begin. Or for the deep nothingness between dreams. Time is relative, personal, different for everyone. And right now, for you, time is slowing, stretching, each moment lasting longer than the last, or seeming to, until moments lose meaning, until time itself fades away. This is the edge, the boundary, the event horizon of sleep. You're crossing it now, or you've already crossed it. Either way, you're gone. Into the quiet, into the dark, into rest. Black holes bend time until it nearly stops. Sleep bends consciousness until it dissolves. Both are natural, both are necessary. Both are part of how things work. Rest now, fully, completely. There's nothing left to do, nothing left to think. Just rest. The universe continues without you. Stars shine, planets orbit, black holes warp spacetime. All of it going on while you sleep. And that's fine. That's how it should be. You don't need to witness it all. You don't need to understand it all. You just need to rest. Your breathing is barely perceptible now. So slow, so soft. Almost not there. But they're still there, keeping you alive while you sleep. Time flows, space curves, the universe expands, black holes exist, and you rest. All of this happening simultaneously, all of this part of the same reality. Somewhere a photon of light is approaching a black hole. It's been traveling for millions of years. Now it's close, bending around the event horizon, following the curved spacetime. It makes one orbit, then another, spiraling closer. Eventually it crosses, falls in, gone. The journey ends. Your journey into sleep is ending too, or has ended. You've arrived. You're here, in the deep quiet, in the stillness, in rest. There's nothing more to say, nothing more to explain. Just silence now, and darkness, and sleep. Time stands still near a black hole. And here now, in your sleep, time stands still for you too. Not literally, time is still flowing. But you're not aware of it. Hours might pass, they might feel like nothing. You might dream 1,000 dreams, or none. Either way, when you wake, time will have passed. But you won't remember it passing. You'll have been elsewhere. In sleep. In dreams. In timelessness. The universe is vast, full of wonders, full of mysteries. Black holes warping time and space. Stars being born and dying. Galaxies colliding. All of it happening. All of it real. And here you are, in your small corner of it. Resting, breathing, baying. That's enough. You're enough. Rest is enough. Sleep now, deeply, peacefully. Let time flow without you. Let the universe continue. Let yourself simply be. Gone. Into sleep. Into dreams. Into the quiet darkness. Where time doesn't matter. Where nothing matters except rest. 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 The black hole waits in silence. You sleep in silence. Both timeless. Both still. Both at peace. Sleep. Sleep. Sleep.